Okay, come on, let's get started. Open your textbooks, please, to page 125. Page 125. So the aim for this week is to try to complete this topic, specific heat capacity. I don't think we can finish the whole topic by this week, but at least I want to cover the theory by this week. There will also be a group project with regards to this particular topic. So actually last Friday I told you guys to do your groups. Then I did share the group link for the spreadsheet, but I didn't announce. I just put it in your Google Classroom, and I think nobody saw it. Never mind. You have until end of today, okay, to key in your names. But I will be letting you know what to do. So the moment you get your groups, you can get started. Okay. But let's learn this topic. Let's get started with this topic first. So at least when you want to start doing your group project, you will be better prepared on how to get started lah. Okay. So open your book to page 125. I don't like how this topic straight away starts with formula. I think that's very confusing. So, but you can refer to your textbook. The module book we will use in a moment. But I'm going to explain this my own way. Okay, I'm going to explain this my own way. But you can refer to the textbook if you need to. So if you want to come in on the Jamboard, do come in here. I'll share with you the link. It's blank at the moment. There's nothing else there, because I want to explain from scratch. Okay. Hey, faster, link copy, go away. I cannot click behind you. I'm trying to click next, and the link copy is blocking my mouse. Hey, nonsense. Okay, so here we go. Okay, so last Friday, we went through a little bit when I was talking about the material and the mass and the heat and all that. That's all related to this topic, yeah? So once you understand how different factors can affect different, the different rate of energy absorption, we are going to focus today on the technical terms. That means now we actually have to learn the terms and the formula. My mistake, I forgot it should be two things: heat capacity and specific heat capacity. I forgot your syllabus, they do two. Last time the old syllabus only one. So that's actually to apply the formula. So just these two, okay? So we're going to start with heat capacity. So on page 125, you can refer, but let me explain this in a simplified way first, okay? So before we go to, because if we go to the definition, sometimes it doesn't make any sense. So I want to explain so that you understand first what the concept is about. Then when you look at the definition, it makes sense, all right? Am I talking to myself? Hello? Is anyone there? Okay, thank you. Put yellow color lah, huh? Can see heat capacity, okay? So heat capacity is very simple. What it means is this. Now let's say we have an object. I'm just going to put one random object. Imagine lah, okay, this is a copper ball. Nice ball, okay. So got we put color lah. Okay, it's a nice copper ball. Okay. Maybe don't put red. Let's put different color lah. Let's put blue color lah. Okay, imagine it's a blue ball. Okay, blue copper ball. So let's say, right, this particular copper ball, we're going to apply heat to it, right? So we apply heat. Now let's say we can measure the temperature. So what happens is if we apply heat, what's going to happen to the copper ball? Is the temperature going to change? Is it going to increase, decrease, or no change? What do you think? It's a very simple question. Not trick question. It's not a trick question. If we apply heat, will the temperature of the copper ball increase, decrease, or not? No change. If we apply enough heat. We apply heat. Increase. Okay. So yes, obviously, logical, good. Everyone who has replied got logic, very good. Okay, so the thing is, right, the more heat we apply, the higher the temperature will increase. Agree? Right? The more heat we apply, the higher the temperature increase. Now, different objects have different rate of temperature increase. Agree? Like if let's say now we get a let's say the smaller copper ball. We apply the same amount of heat, same amount of heat, same amount. Is the temperature increase going the same or different compared to the big one? What do you think? Let's call this A and let's call this B. So if we apply the same amount of heat, will the temperature change be the same or different? What do you think? Different. All right. So heat capacity refers to how much heat energy needed to change the temperature. Again, heat capacity refers to how much heat energy is needed to change the temperature. So logic, how much energy to change the temperature? That means if you want to count, very simple. Let me use text rather than Miss Ho, right? What you do is you calculate the heat energy divided by the temperature change. So the heat energy supplied, let me call this. Okay, heat energy supplied divided by the temperature change. So let me draw the line. Okay, it's a divided by line. Okay, this is the formula for heat capacity. So when you look at this, basically heat energy unit is joules and temperature change is degrees Celsius. That means heat capacity is measured as joules per degree Celsius. Logic. How much heat energy supplied divided by temperature change. I know your book write a bit different. Quantity of heat supplied. Okay, doesn't matter. Change in temperature. Same thing, temperature change. Okay lah, I write according to your book lah, otherwise you get so confused. Why did you write different? Okay. Why this Jamboard likes to do this one? Okay, I call this change in temperature, okay? Change in temperature. So you think, let me put two numbers here, okay? Just for you to compare side by side. If let's say one object has a heat capacity, I put here 1000 joules per, I should write this in SPM style, per degree Celsius. So let's call this object for object P. And object Q has a heat energy or a heat capacity of 200 joules per degree Celsius. What does this mean? If P has 1000 joules per degree Celsius, it means if we want the temperature to change by 1 degree Celsius, you need to put in 1000 joules. That means if you want 2 degrees Celsius, 2000 joules. Compare this to Q. Q, every 1 degree Celsius change, you only need 200 joules. So if you put in, you want to change 2 degrees Celsius, means 400 joules. So we say change in temperature because it's not about what the temperature is. Like right now, let's say 25 degrees Celsius. We don't care what is the current temperature. Because now we're talking about changes. You put in heat, we know when you put in heat, the temperature increases, right? You don't put in heat, no temperature change, right? So you put in the heat, then the temperature go up. How much heat energy needed to make the temperature increase? It can also be the other way. If there's energy release, then the temperature will drop. But usually that one a bit harder to understand. So let's talk about the energy increase, then it's easier to understand. So again, you see this number, P equals 1000 joules per degree Celsius means what? To change the temperature by 1 degree Celsius, there needs to be 1000 joules of energy. So now, based on this understanding, which one needs more heat energy to change the temperature, P or Q? Based on these two numbers. Which one needs more heat energy to change the temperature? P. Correct. Very good, correct. Because the number is higher. Okay, so heat capacity just means this. They don't care whether it's copper or iron, they don't care what material, big or small, don't care. It's just this object, how much heat energy needed to change every 1 degree Celsius. That's all. So let's look at this now, A and B. Let's say A and B both are copper. You think the number for P, is it suitable for A or for B? What do you think? The number for P, is it suitable for A or for B? Let's say we have to, draw the line and cross and try to imagine. P, okay, you say P is suitable for A, okay. So that means B is Q, logical or not? I agree with you. More logic because, yeah, A needs more energy because it's larger. Okay, everyone can follow me so far? Yeah. So, heat capacity, if you had to give the definition, is based on the formula. It is based on the formula. So that's why you look at the formula, it says here, heat capacity is of an object is the quantity of heat needed to raise the temperature of the object by 1 degree Celsius. Don't write the formula out. When you write definition out, write out in words. So I'll just write the definition here as your reference. Alamak, I'm supposed to use the text function. So heat capacity of an object is the, okay, so you don't write exactly also is fine as long as the meaning is close enough. So I'll change the words a bit so that you are aware. It's the amount of heat needed to change the temperature of the object by 1 degree Celsius. Let me get the degree symbol because I cannot tahan the round zero thing. Where's the degree symbol? You know how I'm doing this? I open Google, I type degree, I copy the degree symbol and I paste inside here. Smart, right? Next time you all do that also, okay? So this is the definition for heat capacity. All right? Okay, so that's heat capacity. So now, let's look at the following page, 127. So now you can scribble things in your in your textbook to help your understanding. Or if you're planning to sell your textbook, then you put sticky notes. Okay. Don't simply scribble. Do you know that this library textbook, I borrowed from the school library, you know the previous teacher go and chanting in the book. I cannot believe it. Never chanting library book. Never chanting other people's book. Your own book you chanting, never mind. I know, right? I tell you, I was so annoyed. Okay, so now let's look at specific heat capacity. Now, okay, so as physics students, you must remember that when it comes to technical terms, especially in science, whether it's chemistry or physics, the terms are very, very important. Remember, you take out one word, you change the meaning of the entire sentence. Remember the earlier topic we learned, right? Where you don't put the word net, the whole meaning changed already. Okay, rate of heat transfer is not the same as net rate of heat transfer. You take out the word net, different meaning already. You have to be very careful. You change the spelling also, different meaning already. Okay, physics not so bad lah. Okay, but chemistry is very important because chemistry, you change the number a bit, wrong already. You change the spelling of the chemical, wrong already. Seriously, because there's some chemicals, one letter difference is a different chemical altogether and can have very, very different results. One can be poison, one can be useful. So that one chemistry, I'll let your chemistry teacher explain. Physics, not so vital, but it is still very important. Okay. So you have heat capacity and you have specific heat capacity. Specific heat capacity means what? Wow, so specific. You just remember this way. Specific means specific to the material. Okay. So what I mean by this is is this. Now, if you look at page 127, again, you look at, wow, what's this? The formula so complicated, so mafan. Come, I explain to you in a different way, okay? Okay lah, I have to use a formula. Okay, I write out the formula first. So the formula is, oh, I didn't use the symbol in the previous exercise. Sorry, my bad. Let me, sorry, just backtrack a bit. Sorry, I forgot to talk about the formula. In your textbook, I forgot to explain the formula. In the unit, unit plot symbol. In your textbook, they did this. Heat energy, they put as Q. Nonsense. Miss Ho, change it, please. Q is, Q, like, why they put Q? Like, Q not for queen, meh? How come heat energy, they don't put H? How come they don't put E? I also have no answer for you. I also don't know why. So you just imagine Q represents quantity of heat lah, okay? Quantity of heat. That's why your book keep writing the word quantity over and over again, so it drill into your head. Okay, quantity of heat. Okay, so you write Q for the symbol to represent heat energy. Change in temperature. Now, we know that theta normally can represent temperature, normally. So they write theta here. But your book, you can see they put one triangle here, right? You know what a triangle means or not? Have you learned before in maths? The triangle means what? If you put in the symbol. Have you learned before? IDK. Forgot. Triangle means that the temperature got 3 points. No lah. Okay, theta means, the triangle means this. In maths, triangle means the change in temperature. Change. Triangle means change. Triangle means change. Difference. So we see, right, like for example, in this situation, say heat capacity, we heat up. Let's imagine lah, example lah, example, okay? Example. I have to repeat this many times because some people not paying attention. Example, let's say the temperature initially was 25 degrees Celsius. Then after we heat up, the temperature then becomes 75 degrees Celsius. Okay? What is the change in temperature in this case? What's a change in temperature? Can anyone give me the number? Come, your maths all very powerful one. So this is very simple to you. This is kindergarten maths, right? Because it's too easy. 25 go up to 75 is how much? What's the change in temperature? 50 degrees Celsius, correct? So you see, when you use the formula, you cannot, you see, this bottom part, right? You see your textbook there, they label that change in temperature. So a lot of people ask me, hey, why got so many numbers here? Teacher, do I put 25 or 75 for the bottom part? No, neither. So you see here, when you want to use this formula and it give you change in temperature, you don't write 25, you don't write 75. You write the difference. Whether it go up or go down, never mind. You take the difference in the number. So that means the number you must put in this bottom part must be the 50 degrees Celsius. Triangle here means the change in temperature. Why they don't just write theta? Why they put a triangle? They just put like that. The problem is you put theta. Theta just means temperature. Temperature could be what? Oh, can be initial temperature 25, can be final temperature 75. But that's not what you put inside. You need to put the change in temperature. That means the difference. So in maths, when we put a triangle here, is to let you know you are looking for the difference. You're not looking for the final number. You're not looking for the initial number. You are looking for the difference. Can you follow me so far? So you understand the triangle? Triangle means difference. So you must remember when it comes to heat questions like this, right? We don't look at the temperature for the initial or final. That one is not the focus. We look at the difference in temperature because you apply heat. So the temperature change. You want to see the heat, you apply how the temperature increase, or if the heat is absorbed, how the temperature drop. So what's the actual temperature? Not important. We want to see what is the difference, the increase or the decrease in temperature. That one is important. Okay. So when we now come to specific heat capacity, then you see, alamak, teacher, why the formula got so many things there? Never mind. Let me explain. It's very easy one. Okay. So the formula is this: C equals to Q over M. Walao, got triangle again. Actually, it's like this. The Q is what? Q is the quantity of heat or the amount of heat. So let me write here. Okay, this is the heat energy that we will supply. or absorb lah, or let's say, but never mind, we think about supply first. Okay, the heat energy that is being supplied. Okay, M. M this time is the mass. Mass of what? Mass of the object. And then this one, this one is together. Okay, this one is together. It is the change in temperature. Yeah, change in temperature. Okay, so on the right side only got 3 symbols, Q, M, and the theta. Change in theta. Okay, then you see what is all this nonsense? Why so complicated? Okay, it's like this. Now, you see, right? Let me put the unit in for you. I like to explain using numbers. I hope this makes sense for you. So I'm just going to put in the units here. Heat energy is joules. Mass of object, SI unit is what? What's the SI unit for mass? Kg. I'm just checking what temperature they use. Change in temperature, right? You can use SI unit, Kelvin, or you can use degrees Celsius. Now I'm going to use degrees Celsius first. Kelvin, we put one side. Even though Kelvin is SI unit, degrees Celsius is not SI unit. I know it's not, but for the time being, put aside Kelvin first. Let's focus on degrees Celsius. Why? Because it is more common for us to use degrees Celsius on a daily life. Even when we go to physics lab, degrees Celsius is more common because it's easier to measure. Kelvin is a little bit difficult. I don't think you've learned Kelvin before. Have you guys learned how to convert? Oh no, I think you learned before. Have you learned how to convert to Kelvin before? No. Okay, so since you haven't learned yet, we put one side first. We will cover this one. We definitely have to cover in this chapter, but we put one side first. We focus on degrees Celsius. Later, I explain about Kelvin. Okay. So we learn one thing at a time. We focus, okay, what is specific heat capacity? So it's like this. You see, joules, wow, so complicated. Then you see, in the end, you get what unit? Joules. Let me write here. Joules per kilogram degrees Celsius. So this means what? Okay, let me give you a number here, because if I explain like this, it doesn't make sense. So I find most of us, we understand with numbers. So let me give you an example of a number. Let's say we have an object, and then we count whatever nonsense this is R. Let's say this particular object. Now, the specific heat capacity C. This specific heat capacity is this one. Is this one, okay? Is this one. Is for this C. What is this nonsense? Okay, this nonsense, it's not nonsense lah, it's technical stuff. I know you're struggling to understand. Let's say the number now is 1000 joules per kilogram per degree Celsius. It means what? If you have 1 kilogram of the object, we want the temperature to change 1 degree Celsius. We need 1000 joules of energy. That's what it means. Again, we have 1 kilogram of the object. We want this 1 kilogram to increase 1 degree Celsius. We need 1000 joules of energy. This is different from just now. This one just now, what you see, this one is all heat capacity. It's just, they don't talk about kg, it's just how much heat to change by 1 degree Celsius. Suddenly this one, where got kilogram over here? How come suddenly got kilogram one? Because it's for the material. So you see, specific capacity refers to how much is special for the material. So every 1 kilogram of the material, we want to change 1 degree Celsius, we need 1000 joules of energy. So specific heat capacity is very unique for the material. Whether it's a lot of material or less material, like let's say you have 1 cup of water, or 1 big pail of water, 1 swimming pool full of water, or the ocean of water. All of them is water. Doesn't matter how much water you have. All the water has the same specific heat capacity, because we measure not based on how much we have, it's based on a ratio per kg. You have 1 kg of water, you have to increase by 1 degree Celsius, there's a certain amount of heat you need. So just to share with you, water has a specific heat capacity of 4,200 joules per kilogram per degree Celsius. Okay. Yeah, so the ugly. Let me make this look nicer a bit, okay? Because I rubbed the wrong thing. Hiyo. Okay, come, joules per kilogram per degree Celsius. So you see, this means what? If you have 1 kg of water, you want this water to increase by 1 degree Celsius. Okay? You need 4,200 joules of energy. So whether you have small cup of water, a big cup of water, so big pail of water, okay, the ocean of water, wow, doesn't matter, all of water, all of them, in the end you compare, all these different samples, never mind, each of them I take 1 kg, 1 kg, 1 kg, 1 kg. Doesn't matter how much, each one I take a sample, 1 kg, I compare, all of them will have this same value. So this specific heat capacity, you need to think of it as, oh, it's not about how much we have, it's for the material. So another way to compare, now let's compare this 1,000 joules and 4,200 joules. Now you imagine, okay, this is for the material. So if I compare, let's put this for, this number is actually for, I think, which metal is this? I can't remember which metal. Let's put this metal, metal X. So now you compare metal X and water. We take 1 kg of the metal X, you need to increase by 1 degree Celsius, you need 1,000 joules of energy. If you take 1 kg of water, you want to increase the temperature 1 degree Celsius, you need to put in 4,200 joules of energy. Which one need more heat energy? Metal X or water? For the same mass. Water, correct? Water needs more. So water needs a lot of heat energy before the temperature can go up. Metal X need less heat energy for the same mass for the temperature to go up. So specific heat capacity, that's why when you look at the definition, let me create a new slide here. I type it out for you, okay? Specific heat capacity of a substance is the quantity of heat needed to, I follow the textbook first because it's going to be time already. 1 kg mass of the substance by 1 degree Celsius. The definition here is still, if you look at it, is also based on the formula. Specific heat capacity refers to the substance. Substance means a material, that means it's for water, or for iron, or for wood, or for cotton, or for aluminium, or for glass. It is for the material. It doesn't matter how much material you have. The material, as long as the same material, they all have the same specific heat capacity. Okay, it is the amount of, quantity of heat needed to raise the temperature of 1 kg mass of the substance by 1 degree Celsius. So again, you look at the formula. Specific capacity is C. Is the amount of heat energy for every 1 kg mass every 1 degree Celsius. That's the that's the formula. Definition follows the formula. Can you all follow so far? I don't expect you to understand yet, but can you follow? Okay. Okay, so 3 yeses. The rest all, I don't know yet. I'm always very worried for those who don't respond. Okay, so so what you need to understand is like concept of density. Density is also for the material, You have a lot of material. Let's say like water is 1,000 kilogram per meter cube, or 1 gram per cm cube. Water, you have a lot, you have little bit. The density is the same. So same thing with specific capacity. You have a lot, a little bit. The specific heat capacity is the same. Okay. The property is special, is unique to the material. Unique to the material. So it's not about how much or how little you have. Same material, a lot, a little bit, same value. Just remember that way. It's similar to density. Density is how much mass per volume, right? So that's why you put in water, sink or float. The density, you have like the iron, right? Small iron, big iron, they will still sink. Both of them will still sink. Wood left, you have a wooden cube, a wooden boat. Density is less, it will still float. Specific capacity, also for the material. It's not about how big or how small, it's how much heat every kilogram to increase or decrease 1 degree Celsius. Okay. So with I know we have 3 minutes left just to finish up today's lesson. So you see, right? So now once you understand, okay, let's compare again. Let's compare metal X was 1,000. Now we don't care how much, we just see the material. We compare different materials now side by side. Okay, so now water is 4,200 joules per kilogram per degree Celsius. So now just now you told me, hey, for the same mass, water you need more, 4,200 joules. That means what? That means water needs a lot of heat energy before the temperature can increase. That's why it takes a long time for water to boil. You try and see. So you see, so that means that's why you see water takes a long time to boil. Because why? Water has, this number is considered high, 4,200 joules is considered high. It needs a lot of heat energy for the water to increase. But metals have a low heat, low specific capacity. So a little bit of heat energy, wow, become hot already. So what does this tell us? This tells us that if the number is higher, means what? Oh, no, sorry, let me rephrase this way. If the number is lower, means what? Is it a good or poor heat conductor? What do you think? Imagine the temperature go up fast. So is it a good or poor heat conductor? Correct. They are good heat conductors. So this is the relationship. Good heat conductors have low specific heat capacity. The lower the number, the faster the heat increase. That's why they are good heat conductors. Higher numbers will be poor heat conductors. Okay, does this make sense? See you. Bye-bye. Be good. Don't lick anyone's eyeballs. Take care. Have a good week ahead.